Okay, welcome to the next section. This is where we will get more into detail of the actual hardware, the hardware setup. I will first describe the ESP8266. That is the microprocessor that is integrated into the that module that sits on the d1mini board. The ESP8266 is manufactured by a company called Expressive, a Chinese company. They released it quite a number of years ago, and became very, very popular because it was very cheap. This is the chip itself. It's a 32-bit package, 32-pin package. There is obviously a 33rd pin, which is a ground plane that sits behind you that gets effectively for cooling and good grounding. Okay, these are the specifications. As you can see, it's an extensor, 32-bit microprocessor, has Wi-Fi, 2.4 gig Wi-Fi that can handle both an access point or a client. Has integrated TCP/IP stack, so it can do networking and things like that. Has RAM. Has a SPI interface to support external flash memory, which is where the software gets stored. It has a number of GPIOs, which can be configured for many different functions. One ADC. And then these 16 GPIOs, as I'll show in the next slides, can be configured as SPI, I2C, Uart interfaces. This is the overall block diagram inside the ESP8266. As you can see, this is the RF front end for the Wi-Fi. You then have a CPU, and these are your digital interfaces. You have your SRAM, and there's a power management unit. The ESP can be put into sleep mode, and then it can be woken up, and so in that way you can save a lot of power, have battery operated devices. This is more details of the actual pins. You can see a lot of them are power pins, ground pins, and then so this is the 32 pin package. What happens then is this chip is integrated into a module. There are a lot of different form factors, but this is the most common. It's a 16 pins. Well, these 16 are these ones on the bottom are not generally used. They're used internally to integrate to the flash RAM. You can see this is almost like an internal view of what's underneath that can. The chip sits over here, and then you have the flash memory, 4 megabit flash memory, and then you'll see these are the ones on the side are the generally the most used inputs and outputs. This is a schematic essentially of what's inside. Underneath the can there's a crystal, usually a 26 megahertz crystal. There's obviously some capacitors for decoupling, an LED, and then this is your flash memory, and these are the outputs that come out to the outside world. Okay, I'll get more into detail now on the d1mini, which now takes that module package and then provides other circuitry so that you could use it in your circuits. So here's again a picture of what the overall module looks like. This is the metal can, I guess, for shielding. That's that little blue LED there, and then this is your Wi-Fi antenna. Here is now more detailed of the outside of this module, often called a ESP12, and then you get E's and F's and different versions over time. So you can see here you have a reset pin, analog to digital pin. You have a number of GPIOs, in which case these are used for SPI. This is your power pin, 3.3 volts. You have a ground pin, and then you'll see this is your TX and RX for your Uart. That's normally wired to a USB to serial converter and used for flashing code into the device through a USB port. This is R2C, your clock and data line. And then as I said, most of these outputs have a GPIO number, and that GPIO number can be set into different modes in software. This is, I think I showed in the introduction, this is the actual WeMOS d1mini, and now that takes that module, adds some circuitry on the bottom. Here is your USB, here's your micro USB connector where you'd plug it in. There's a reset switch over here. You have some resistors and capacitors and a voltage regulator that'll take the 5 volts and create a 3.3. This is a CH340 USB to serial chip. So yeah, now what you would then do is you would have headers that would go either side here, and depending on the type of header you used, you could connect to you can stack these on top of each other. This is a circuit diagram of the actual d1mini module. You can see there's the 2 lines of outputs, or 2 plugs, 8 pins on each side. This is your regulator. This is the actual module itself, the ESP12F. You have a number of resistors and capacitors that allow the device to be configured as to how it boots. This is your USB connector, your crystal, and then you have your USB to Uart chip, and then these components allow the USB device to control the actual boot mode. So that makes it very useful. You'll see later on, when you flash, you don't need to press the reset pins or do anything. It does it all automatically. Here's another view of the 2 headers with the actual, now the signals coming out into the outside world. Okay, I'm just going to give a brief view of some of the interfaces. This is R2C protocol. It's a multi-drop protocol developed by Philips, or patented by Philips. It's IIC, which is inter-IC communication. It allows you to have generally one master and a number of slaves, but you can have multi-master. This is a clock line and a data line, and you can see this is sort of an idea of how the R2C protocol works. Then the other interface that's supported is SPI, so it's serial peripheral interface. That allows you to have, again, a master-slave role, but you can have one master and many slaves. The advantage of SPI over R2C is that it's much faster. It's more a synchronous clock, so you can have a high-speed clock, and then you have a data in, data out. So you can see the out goes from one device into the next device into the next device, like a chain, and then you can use the chip select line to indicate which device you're actually talking to. So there are a number of SPI formats, basically different ways of the clocking scheme, and whether it's active high, active low. Okay, then the other interface is a Uart. I mean, this has been around forever, so it's an RX-TX line, generally crossed over. So this effectively, not really so much a master and a slave, but you have one device communicating with another device, but the TX talks to the RX, and this TX talks to that RX. The Uart protocol works at sort of baud rates. There's standard baud rates. Often 9600, 115, 200. You have a scenario where it's called asynchronous because it's driven by clocks. So what will happen is you have it's normally idle high, and then on the first edge that tells the receiver that there's data coming, and then what it does is it clocks at certain bit times, which is how the baud rate works, so that it samples in the middle of each bit. So you have often, the most common is sort of 9, 6, 8 bits, one stop bit, because you can see as your stop bit. But in the olden days they used to use 2 stop bits and even odd parity and things like that, because in those days the communication channels were not as sophisticated as we have today. And then sort of lastly we have the Atd converter. The actual Atd converter inside the ESP only has a range of 1 volt, so they normally have to add this divider to allow you to have a 3.3 volt input here. What the Atd converter does, it's an analog to digital converter, effectively takes an analog signal which would now vary between 0 and 3.3 volts, and it will digitize it. So you would, at a certain sample rate, you would digitize every single point on this waveform, and it allows you to then take analog signals like microphones and convert it into a digital signal, or battery voltages and things like that, and then these digital signals can then be processed. Alright, well that's that for this this section. The next section I'll cover the d1mini shields, the OLED display, and the temperature sensor, the Dallas DS18B20.